Good evening to all of you. This is once again Navin Sharma. So, continuing discussion on quantum mechanics part 2, which belongs to BSc Physics course, 6th semester paper 8. This is my session 10. And in this session, I would like to discuss about one more application, the last application of Schrodinger's equation as per our syllabus. So, it is the application of Schrodinger's equation to another system, physical system, which is what we call it as rigid rotator. So our objectives of this particular session is to apply Schrodinger's equation to a rigid rotator. We shall try to understand what is the meaning of rigid rotator, a classical rigid rotator, and then we shall try to apply Schrodinger's equation to that such a particular type of system. And like in the previous case, hydrogen atom, we are going to end up with two different equations. Of course, we are not solving those equations completely, as they are mathematically slightly difficult. We are going to mention the expression for the energy eigenvalues of the rigid rotator. So, aim of our discussion is to apply Schrodinger's equation to a rigid rotator and to see how we can simplify those equations. Although we are not solving the equations completely, so we are going to write down the expression for the energy eigenvalues of the rigid rotator. This is what so objectives of our this particular session. Let us see what is a rigid rotator. So it is a very simple physical system. So in which there are 2 point masses joined together by a rigid massless rod. So which is what we call it as a rigid rotator. So here we're going to consider two particle systems. We are assuming that the two particle systems are so joined together by a rigid massless rod. So it need not have to be a rigid massless rod always. It can also be something like a system in which two atoms are bonded together by a rigid bond. Although a rigid bond is ideal is an ideal case, but still for our discussion we are assuming that the bond that exists between the two point particles or two atoms, whatever they may be, so is a rigid one. So basically, so our rigid rotator is something like a dumbbell in which at the two ends there are going to be two masses, and the dumbbell is actually connected by a hard rod, such that irrespective of the rotation of the rigid rotator, so the distance between the two masses, two particles, would always remain the same. So this is what the meaning of rigid rotator for us right now. So we can conclude, so 2 point particles joined together by a bond or massless rod, such that irrespective of the rotational energy or the rotational angular velocity of the rigid rotator, so the distance between the two particles would always remain the same. Even though the particles may be rotating very rapidly, so still, so there's no change in the distance between the two particles. Now let us consider we have 2 point masses, two particles, so which are having mass m1 and m2. Not written the diagram here, but still it is possible to imagine for us. So we are assuming 2 point masses, so their masses we are considering as m1 and m2, and they are actually joined by a rod of length r, and we are assuming r is constant. So that is what the meaning of a rigid rotator. Now let us assume that the two masses are rotating like a dumbbell about an axis passing through the center of mass normal to the line joining the two masses. They are assuming, so our rigid rotator is undergoing rotational motion. And the rotational motion is about an axis, so passing through their common center of mass. And of course, so the direction of axis of rotation is actually perpendicular to so the line joining the 2 point masses. Now, using your simple Newtonian mechanical rules, we can say that, so if R1 and R2 are the distances, here we are assuming that R1 and R2 are the distances of the two particles from the center of mass. For example, if the first particle is at a distance of R1 from the center of mass, and we are assuming that R2 is the distance of the second particle from their common center of mass. So definitely we can say that since the bond is rigid, we can say that the total distance between the two particles r is equal to r1 plus r2. That is very trivial. Also, with respect to the common center of mass, so we can write this particular condition. So the product mass and distance of the particles must be the same. That is, m1 r1 must be equal to m2 r2 about the common center of mass. So using these two expressions, it is possible to find out moment of inertia of the system. So for our two particle system or the rigid rotator, since it is undergoing rotational motion, we are interested in the moment of inertia rather than the individual masses m1 and m2. So therefore, we need to find out an expression for the moment of inertia of the rigid rotator system. So the moment of inertia of the rigid rotator, so is simply capital I simply equal to moment of inertia of the first particle plus moment of inertia of the second particle with respect to the common center of mass, or with respect to an axis of rotation that is actually passing through the center of mass. So therefore, moment of inertia of the first particle is actually given by m1 r1 square. So the moment of inertia of the second particle with respect to the axis of rotation is given by m2 r2 square. So since it is a rigid rotator, it is a dumbbell two particle system. So therefore, the total moment of inertia of the entire system is simply equal to the sum of the moments of inertia. So therefore, the total value of the moment of inertia is given by capital I is equal to m1 r1 square plus m2 r2 square. We can do a simplification here. We can use this expression m1 r1 is equal to m2 r2, and also we can use the relation r1 plus r2 is equal to r. What we can do is, I've not shown those mathematical steps here, but it is very easy to show that. Using these two expression m1 r1 is equal to m2 r2 and r1 is equal to r1 plus r2 is equal to r. So we can eliminate any one of the quantities, let us say r1. We can eliminate r1 and we can find out an expression for r2. And that expression for r2 can be substituted here. Similarly, using these two equations once again, we can eliminate r2 and we can find out an expression for r1, and that expression for r1 can be substituted here in m1 r1 square. If we do that little mathematics, so then we can show that this equation actually reduces to a form equal to m1 m2 divided by m1 plus m2 into r square. Essentially, what we have done is we have eliminated r1 and r2. We have expressed r1 and r2 in terms of r. So the total distance between the two particles, or the length of the bond, or the length of the rod that is actually present between the 2 point masses. So therefore, we have expressed in terms of r. If we do that one, then we are going to end up with this kind of equation: m1 m2 divided by m1 plus m2 to the times r square. Now this ratio m1 m2 divided by m1 plus m2 is something like has a dimension of mass. So this quantity m1 by m2, m1 m2 divided by m1 plus m2 is what we write it as mu, and this mu is what we call it as reduced mass of the rigid rotator, or reduced mass of the system. So therefore, we have found out an expression for the moment of inertia of the system. Moment of inertia of the system, or moment of inertia of the rigid rotator, is given by mu into r square, where mu is called as the reduced mass of the system, and it is given by m1 m2 divided by m1 plus m2. Essentially, so what we have done here is we have converted two particle system into one particle system. Instead of considering two particles m1 and m2 of masses m1 and m2 separated by a distance r, it is possible to consider one single particle of mass m1 m2 divided by m1 plus m2, that is nothing but mu, that is what we call it as reduced mass of the system, which is situated at a distance r, so from the one particular point of reference. So essentially, this problem what we have done here is reducing the two particle system into one particle system, and that reduced system has a mass of m1 m2 divided by m1 plus m2. That's why this particular quantity is what we call it as reduced mass of the system. Now, that is what I have written here. You can thus replace the rotating dumbbell base in the point mass mu at a distance r from the axis of rotation. Instead of considering two particles which are separated by a distance r, it is also possible to consider one single point mass having mass of mu, reduced mass, at a distance r from the axis of rotation. So that is what I explained so far. So that is what we have done here. So reducing two particle system into a single particle system. Now we can take the potential energy of this particular system as a zero. The reason for the this particular answer, mean the potential energy of the system is zero. It is because the 2 point masses are rigidly joined together, so their distance always remains constant. So therefore, we can assume for such a system the total potential energy is zero. So therefore, we have a system of rigid rotator in which two particles are so joined together by a rigid rod of fixed distance or a rigid bond of constant length. In such a such a rigid rotator system can be reduced to one particle point system. So therefore, so now we are ready to solve the Schrodinger's equations for this particular system. So again, because of the spherical symmetry that the system is possessing, we are writing the Schrodinger's equation in terms of spherical polar coordinate, just like the previous case, hydrogen atom. So even here, since with respect to the axis of rotation, the whole system, the rigid rotator, actually possesses spherical symmetry. So therefore, we need not have to write Schrodinger's equation in terms of Cartesian coordinates. We can follow the same thing that we did in the case of a hydrogen atom. So therefore, we can write the equation, Schrodinger's equation in terms of spherical polar coordinates. This is the same old equation that we use in the case of hydrogen atom. So it is 1 by r square dou by dou r of r square of dou psi by dou r plus 1 by r square sin theta dou by dou theta of sin theta of dou psi by dou theta plus 1 by r square sin square theta dou square psi divided by dou phi square plus 2 mu by h cut square e minus 3. So times psi is equal to 0. What we have done here, we have made a small change here. Instead of small m, mass of the single particle system, we have written it as mu, because in the case of rigid rotator, so the mass of the rigid rotator must be actually replaced by the reduced mass. So one reduced mass is nothing but mu. So therefore, in the place of m, we have written as nu, so the reduced mass of the system. So that is what one thing we did a change here with respect to the case of hydrogen atom. Even in the case of hydrogen atom, we need to go by the the reduced mass of the system. But in the case of hydrogen atom, so compared to the mass of the nucleus, there is a proton, mass of the electron is too small. So therefore, we did not do that kind of approximation there. Actually, so in order to obtain correct eigenvalues of hydrogen atom, we need to include reduced mass of the system, reduced mass of the hydrogen atom, even in the case of hydrogen atom. But anyhow, here, since we are considering two particles of comparable masses, so mass here should not be either m1 or m2, it should be mu. So the reduced mass of the system. So therefore, Schrodinger's equation as applied to rigid rotator is given by this particular expression. Now there are certain changes we need to make here. The first thing is, since we are assuming the system is a rigid rotator, so therefore the distance between the two particles would always remain constant. So therefore, r is a constant here in this case. Since r is a constant, so this first term in the equation 1 by r square dou by dou r of r square of dou psi by dou r can be neglected, can be left out. This basically because as r is constant, our wave function psi is actually independent of r coordinate. So there is no dependency of the wave function on r coordinate because r is constant for the case of rigid rotator. So therefore we can forget about the first term. So therefore we can say that in the case of rigid rotator, the first term of this particular equation vanishes as r is constant. And also I mentioned, so since the 2 point masses are joined together by a rigid bond, so therefore the potential energy of the system is also 0. So therefore we can substitute. So V is equal to 0. Moreover, not only the reduced mass of the system here, the reduced mass of the system mu should actually be replaced by I, the moment of inertia of the system. So after doing all these changes, so we are going to end up with equation something like this. 1 by sin theta dou by dou theta of sin theta of dou psi by dou theta plus 1 by sin square theta dou square psi divided by dou phi square plus 2ie divided by h square psi is equal to 0. This is what the equation we are going to get once we simplify this equation by forgetting the first term and by replacing mu reduced mass by I, moment of inertia of the system, and also substituting V is equal to 0. And of course, there is 1 by r square term here. So r cannot be equal to 0. So therefore, after eliminating 1 by r square term in these three terms, we are going to end up with this type of equation. So 1 by sin theta, dou by dou theta of sin theta dou psi by dou theta plus 1 by sin square theta, dou square psi divided by dou phi square plus 2ie by h square psi is equal to 0. Now here equation 3 is a equation in which we have a wave function which is function of two coordinates theta and phi. And this equation actually can be solved again by the method of separation of variables. So two variables theta and phi can be separated out and they can be brought in two different positions. They can be equated to some constant and it is possible to solve those equations. So that's what I have written here. Wave function psi is no longer a function of r because r is constant, we have eliminated it. So therefore psi is a function of theta and phi. So this wave function, which is function of theta and phi, can be written as a product of two separate functions. So each of only one independent variable theta and phi. For example, psi of theta and psi of theta comma phi can be written as theta of theta and phi of phi. So this is capital theta and this is capital phi. Capital theta function is a function of theta, small letter theta. Capital phi is a function of, so this coordinate phi coordinate small letter, which is denoted by small letter. So therefore, we are segregating this equation into two different terms, two different functions, wave functions. The first function being the function of only the theta coordinate. The second function being the function of only the phi coordinate. So what we had to do is we had to substitute equation 4 back into equation 3. And afterwards, we are going to divide that entire equation by theta phi divided by sin square theta. So we have to substitute psi is equal to theta phi here in the equation. And after doing that, we have to divide that entire equation. So by theta phi divided by sin square theta. And if you rearrange, if you do this little bit of mathematics, then we are going to get sin theta divided by theta, sin theta by theta, capital theta, d by d theta of sin theta, d theta, capital theta divided by d theta, plus 8 pi square ie divided by h square sin square theta, and that is equal to 1 by 5 into d square phi divided by d phi square, the numerator phi being the capital theta. So this is what the equation we are going to get after substituting equation 4 in equation 3 and doing this division theta phi divided by sin square theta. So then we are going to get this equation. So that equation is what I have written it as equation 5. Now here, observe carefully. So there are two terms here. On the left side of the equation, we have two terms. And the right side, we have one single term. On the left side, so the two terms are purely functions of the coordinate theta. Whereas the right side, all the terms of this entire terms, actually they are functions of phi, another coordinate phi. So therefore, a pure function of theta is actually equal to pure function of phi. That is possible only when these terms are equal to a constant. So therefore, equation 5 must be equated to a constant, and that constant is some number. Let us proceed. So the above equality implies that each side must be equal to a constant. It is convenient to call this constant as m square. Therefore, differential equation for the function theta and phi r. What we are doing is we are equating them to a constant. That constant we are calling it as m square. And if we write equals to m square in equation 5 and do the simplification, then we are going to end up with the two equations. The first one is 1 by sin theta d by d theta of sin theta d theta by d theta plus 8 pi square ie by h square minus m square divided by sin square theta of theta is equal to 0. There is a theta square in the right side, and if you bring it to the left side and combine with these sin theta terms, then we are going to get a equation of this particular form. And we are going to get the second equation. Observe here. So the second equation is minus 1 by 5 d square phi divided by d phi square that is equal to m square. And again, if we simplify the particular equation, we are actually going to end up with the second equation, d square phi divided by d phi square plus m square phi is equal to 0. So this is our equation 7. So you can remember that equation 7 actually resembles the same type of equation that we got in the case of hydrogen atom. We call it as something like azimuthal equation. So the azimuthal equation in the case of rigid rotator is actually same as the azimuthal equation in the case of hydrogen atom. In the case of hydrogen atom, we wrote this constant as Ml square and we called it as magnetic orbital quantum number. Here in this case, it is some other quantum number. So we're not calling it as a magnetic orbital quantum number. It's simply equal to some other quantum number. So therefore, that quantum number is nothing but m. So the constant is not m, actually it is m square. So therefore, these are the two equations. Now, equation 7 can be solved easily in the same method that we did in the case of hydrogen atom. We're not going to do all those mathematical details here. We shall try to avoid the wave function form of the rigid rotator here. We are only interested in the energy eigenvalues of the hydrogen atom, the rigid rotator. So therefore, so we can something like summarize our discussion. So equation 6 can be solved. Equation 6 can be solved very easily. And the equation 6 can be solved only when, so the term that whatever we have written here, 8 pi square IE divided by h square, so that must be equal to another constant. And that constant is actually given in the form of j into j plus 1, and j is what we call it as rotational quantum number, because it can take only a discrete set of values 0, 1, 2, 3, etc., etc., etc. So therefore, we can conclude that equation 6 would give us some valid solutions, would give us some valid form of the wave functions only when this 8 pi square IE by h square must be equal to a constant. That whole constant we are writing in the form j into j plus 1, where the possible values for j can be either 0, 1, 2, 3, etc., etc., etc. And we are calling j as the rotational quantum number because it is a quantum number which is associated with the rotatory motion of the rigid molecule. So therefore, we are calling j as the rotational quantum number. So what I have mentioned earlier, so we're not going to discuss the solution of this equation completely. We are just mentioning that these equation would give us some proper solution only if this condition is satisfied. 8 pi square IE by h square must be equal to j into j plus 1. J is what we call it as rotational quantum number. And using this equation, it is possible to write out the expression for E. So we can send h square to the right side and 8 pi square I to the right side. And if we do that, and please observe here, E, energy of the rigid rotator, is a function of J, the rotational quantum number. So therefore, instead of simply writing E, we are writing it as EJ. So EJ, energy of the rigid rotator, so which is depending upon the rotational quantum number state, is given by h square divided by 8 pi square I into j plus 1. So this is what we call it as equation 8. And equation 8 actually represents energy eigenvalues of the rigid rotator. So therefore, we can conclude. So we are able to obtain, although not completely, we are able to prove that. So the rotational energy states of a rigid rotator are also quantized, just like energy levels of hydrogen atoms are quantized. So I can just give one small thing that we discussed in the case of hydrogen atom. Even in the case of hydrogen atom, energy eigenvalues in the hydrogen atom were quantized. They were actually dependent on n, so the principal quantum number. And here, just like the previous case, the rotational energy levels of a rigid rotator are also quantized, and they are actually dependent on this j called a rotational quantum number. The possible values of rotational quantum number are 0, 1, 2, 3. Unlike the case of hydrogen atom where n is equal to 0 is not possible, whereas so j is equal to 0 is possible in the case of rigid rotator. So therefore, I can conclude that the equation 8 actually represents the energy eigenvalues of a rigid rotator. So clearly we can say that j is equal to 0. Substitute j is equal to 0. That is what actually corresponds to the lowest energy state. The substitute j is equal to 0, Ej becomes equal to 0. So therefore, we can conclude Ej, the lowest energy state of a rigid rotator, is 0. So that means, the ground state of a rigid rotator is a state in which the two molecules or the two atoms or the two point particles are not at all rotating. They are staying in the state of rest. Then only Ej would become actually 0. This is quite an important result. Actually, this result actually can be compared to that of a linear harmonic oscillator. So if you compare this one with a linear harmonic oscillator, In the case of linear harmonic oscillator, we had something like vibrational quantum number, and the least energy state of a linear harmonic oscillator actually corresponds to vibrational quantum number being equal to zero. But when we substitute the vibrational quantum number is equal to zero, so the total energy of the lowest energy state of the linear harmonic oscillator doesn't come out to be zero, it actually comes out to be half ht naught. That is what we called it as 0 point energy of the oscillator. And we told that 0 point energy of the oscillator is not zero, even if we approach 0 Kelvin. But unlike the case of your linear harmonic oscillator, the rigid rotator is actually matching with the classical result, which says that when J is equal to 0, Ej is also 0. That means our rigid rotator is not at all rotating. That actually corresponds to the ground state. Similarly, if I substitute J is equal to 1 here, then we are going to end up with energy of the first excited state of the rigid rotator. If you substitute J is equal to 2, we're going to get E2, energy of the second excited state of the rigid rotator, and so on. And clearly, by looking at this form J into J plus 1, we can conclude, although not written specifically, we can conclude that the rotational energy levels of a rigid rotator are not equally spaced. And again, unlike the case of linear harmonic oscillator. In the case of linear harmonic oscillator, so the vibrational energy levels are equally spaced, whereas in the case of a rigid rotator, so the rotational energy levels are not equally spaced, they are actually spaced unequally. In fact, as the value of J increases, the separation between the energy levels also increases. And this also can be written graphically using the energy level diagram, which I have not done here. I'm not going to do it. But anyhow, that is very clear from the form of the equation 8. So therefore, let me come back to my objectives. So we discussed one more case of application of the Schrodinger equation to a system called rigid rotator. And we assumed that rigid rotator is a system consisting of two particles which are separated by a constant distance. Although this is not rigorous, but anyhow, for